My name is Martin and I will be presenting the work Semantic Patches for Adaptation of JavaScript Programs to Evolving Libraries, which is joint work with Benjamin and Anders. So let's first consider the motivation for this project. Node.js is a widely used platform for software development, and its dependency management system, NPM, is the largest package registry in the world, with more than 1.5 million packages, some of which have more than 45 million weekly downloads. Third-party packages are used extensively in Node.js applications, with typical applications having more than 50 dependencies. While the large degree of reusability in the NPM system reduces development costs, it also gives rise to several new challenges. One of them, which I will describe through a small example. So consider the scenario where a package A depends on version 1 of the package B. A new and improved version of B is released, and the developer of A decides to upgrade. But backwards incompatible changes, also known as breaking changes, are introduced in the new version of B, and the package A breaks. The developer of A is now left with the challenge of finding the locations in A affected by breaking changes, and then adapting them to the new version of B. This is the challenge which we will now consider. We have developed the tool JSFix, which through a three-stage process semi-automatically allows a developer to upgrade dependencies in the presence of breaking changes. This figure shows an overview of the JSFix tool. A user program initially depends on version 1 of the library lib, but after the JSFix tool has run, it is modified to depend on version 2, and all breaking changes in the new version of lib have been addressed. In the first step of JSFix, the program is processed by an analysis phase that finds locations in the source code affected by breaking changes. A lightweight static analysis described in an UPSLA paper from last year is used in this phase. But the analysis over-approximates, so it may mark too many locations. Since attempting to patch unaffected locations may be just as bad or worse than missing affected locations, a second phase is used to remove the false positives. In this phase, JSFix will ask the user questions that allow it to remove the false positives. These questions do not just take the form of, is the match a false positive, but rather they are about properties of the program code, such as, is the variable x of type t? The questions take yes/no answers, making them easy to answer quickly. A nice property of the static analysis from the first phase is that it categorizes affected locations as having either high or low confidence. Since all potential false positives are among the low confidence affected locations, questions are only asked for those. In the third and final phase, the affected locations are transformed to be compatible with the new version of the dependency. JSFix uses a collection of so-called semantic patches to both identify affected locations and transform them. A semantic patch consists of both a detection pattern consumed by the first phase and a code template consumed by the third phase. The semantic patches are handwritten by someone familiar with the breaking changes in the dependency, for example, the developer of lib. We'll see an example of a semantic patch on a later slide. I will now show a demo of the JSFix tool. JSFix takes as input a URL to some repository containing dependencies that we want to update. Let's input such a repository. We see that JSFix supports updating 2 dependencies in this repository. Let's select the RxJS dependency, and then all of the files that we want JSFix to consider. In this case, the files in the source and test repositories. We start the tool and see that JSFix has generated a total of 14 questions, which we have to answer. Let's consider the questions in the logic wrapper file. The first question here is whether the receiver of this expression is an RxJS observable. The answer here is yes. After entering the remaining 6 questions of this file, JSFix will run the transformation phase, and we will get a diff showing the changes made by JSFix, which we can then confirm. After entering all of the questions and confirming all of the changes made by JSFix, we are taking to a place where we can create a pull request, which will only take a couple of seconds. And then we get a URL pointing to the pull request with all of the changes. And if we inspect the changes made, we see that JSFix has made all of these changes just from entering 14 questions. Let's see an example of a semantic patch addressing a breaking change in the RxJS library concerning drop support for chaining operators. It consists of two pieces: a detection pattern consumed by the first phase of the analysis, and a code template consumed by the third phase of the analysis. At the bottom, we see a diff resulting from the transformation described by this semantic patch. The detection pattern identifies calls to the map and debounce time functions on objects originating from the RxJS library. In the example here, act is such an object, and debounce time is called on it. So the first phase marks the highlighted node as a match. In case the analysis were too imprecise to determine the type of act, the user would have to answer the question, is the receiver an RxJS observable? Let's now consider how the transformation is applied. First, $base is a special variable referring to the receiver of the identified call, so it's replaced with act. Then a call to pipe is inserted. The argument to this call is $prop imported from the module RxJS operators. $prop is debounce time, so debounce time is imported from RxJS operators and inserted. Finally, the argument to this call is $args, referring to the arguments of the original call, which in this case is debounce. The code no longer uses chaining operators, and the breaking change has therefore been addressed. We evaluated JSFix by entering 3 research questions. The first of them is how many breaking changes in top NPM packages can be expressed as code templates. For this research question, we considered 12 major updates of widely used libraries with 186 breaking changes in total. We wrote 326 detection patterns and accompanying code templates for 298 of them. For the remaining 28 detection patterns, we could not write code templates for 7 of them due to limitations with the template language, 19 of them because no general patch was possible, and 2 due to missing details about the breaking changes. So in conclusion, we could successfully write code templates for more than 90% of the detection patterns. The second research question is, can the applied transformations fix broken test suites, and are client developers willing to accept the transformations as pull requests? For this research question, we considered the same 12 major updates again. We extracted a total of 89 clients, for which the test suites succeeded before the update, but failed afterwards. In other words, clients that are certainly affected by breaking changes. We ran JSFix on these clients using the semantic patches written during the previous experiment. After running JSFix on these clients, 82 test suites succeeded, 2 still failed, and 5 could not be updated since they were affected by breaking changes not supported by the semantic patches. So in conclusion, the JSFix transformations made 92% of the client test suites succeed. We also conducted an experiment where we created pull requests with the JSFix transformations. 31 of these have been accepted, demonstrating that the transformations made by JSFix are generally of a high enough quality to be accepted as pull requests. Finally, the third research question is, how many and of which type of questions do JSFix ask? Where the answer is less than 3 questions per client on average. So to conclude on our work, we present a novel technique for adapting clients to new dependency versions in the presence of breaking changes. Our technique handles 90% of breaking changes, produces transformations that fix more than 92% of test suites, and produces transformations which clients are willing to accept as pull requests. The key ideas are using a lightweight static analysis for identifying affected locations, an interactive phase for filtering false positives, and a simple template-based language for describing transformations. We will have an online version available soon, and a technical description can be found in the paper.
Please let me know, Martin, when it says you are live.
It says I'm live now.
Okay, hello everybody. This is Davide Falessi, and we are here with Martin Thorpe and Benjamin Nielsen that presented this great paper and are ready to answer all your great questions. So the first question is from Sridhar, and it is, how did you arrive at the breaking changes and semantic patches? So did you find that the changes are related to syntax, semantics, or some other kinds of changes?
All right, good question. Thank you for that. So actually, the set of breaking changes that we consider in this paper are from the previous, or the paper from last year, the UPSLA paper. And the way we arrived at them was just by going through top NPM packages and examining their changelogs. We took the latest major version for each of these top packages. And then we just went through the bullet list of changes. And of course, this is not necessarily a very standardized way of doing it, because some bullets may contain lots of changes and other bullets may contain very small changes. But basically, just, I guess the dual answer is just that we found the breaking changes by examining the changelogs. And whether the changes are related to syntax, semantics, or other kinds of changes, it's a bit of both, actually. So a lot of them are, I guess, what you would call syntactical changes, where you rename a method. But we also have more advanced stuff where we have to take a return value from some method and then change it a little bit to make it compatible with the old version of the library or the dependency. So it's a bit of both. We don't have any specific numbers on how many of them are syntactic and how many of them are semantics.
Mm-hmm. So the next question is from Geok, and it is it only possible to describe syntactic patterns in semantics patches? If not, which kinds of semantics patterns could be represented in semantic patches?
Well, it is only possible to describe syntactic patterns, but that doesn't necessarily mean that it cannot handle semantic changes. Mm-hmm. Because, as the example I gave before, we can write a semantic patch that, for example, wraps some function call and then transforms the return value. That would be one example where we actually change the semantics. I hope that makes sense. If I'm not sure I understand the question. If that is,
I think it's good enough as an answer. So the other question is that in phase 2, is there a template for questions as well? How are they generated?
It's a bit of both. So some of the questions are auto-generated. So the ones that are related to, for example, the types of a function argument, we can auto-generate those. And some of the other ones have to be provided by whoever writes the semantic patches. And there is generally no template for that. You can pretty much just write whatever kind of question you want.
Okay. Felipe is asking, which additional breaking changes can the tool identify beyond the API changes?
So it's sort of designed to make changes at this boundary between client code and dependency or library code, which of course means that it's changes that take place at like this API boundary. So we are currently investigating whether we can extend the tool to handle more general refactorings, or maybe trying to patch certain security problems. But this version of the tool that I presented in the paper is only for changes at the API boundary.
Geok asks, do you think that it is also possible to automatically synthesize or generate even semantics patches by using static analysis tool for updated library themselves? Is it one of your future work?
Yeah, it's a very good question. It's something that we have definitely been considering. So one of the challenges with doing that is when working with JavaScript or Node.js, it's really difficult to statically actually decide what is the API of some library. And the reason for this is that you can use, or you often use, reflective patterns to set up the API at runtime. So this is, from a static analysis perspective, quite challenging to do. It's really difficult to get a diff of two versions of the library and then decide which parts of the API have changed. But we have previously been looking at this. We have previously designed this tool called No Regrets, which was presented at eCube in 2018, which can actually determine the API changes that take place in two versions of between two versions of a library, and it's possible that we could use the results from that tool to automatically generate semantic patches, at least some of the semantic patches. The ones that are, I guess, the simpler ones that are related to renames and so on could probably be auto-generated. Okay, there are still almost 3 minutes of time, so I'm asking all the 63 attendants to write a question. My question is there any context where we should particularly prefer or avoid the use of your approach somehow? Any context where we should avoid using it? Yeah. Or where you think it will be particularly accurate or particularly inaccurate somehow? Well, I guess it could be used pretty much everywhere. There are certain types of changes that are not handled. So, for example, if a library developer says that suddenly he doesn't support Node version 6, for example, he only supports newer versions. That's not something we can handle. Okay. But they do understand that it cannot handle it, so it doesn't do anything crazy, right? No, the current version will just so in this demo you saw I create this pull request, and the current version will just state specifically in this pull request that this update no longer supports Node version 6, for example. So the library developer knows that, or the client knows that he has to ensure that this is handled somehow. Okay, the last question, since there are no other questions. My last question is that I think there actually are other questions out there. Oh, sorry. How are these to write semantic patches in practice? Right, that's a very good question. So in our experience, writing the semantic patches is actually quite simple once you understand what the breaking change does. So understanding the scope of the breaking change can be really difficult. And that's because library developers have very different ways of writing these change logs. So in one change log, it may say specifically that all of these methods have been renamed to something else. Whereas in another change log, it may say that there are a lot of changes around this part of the API. And then it's up to the user to determine what is actually going on. So I would say that once we actually understood the changes, writing the semantic patches didn't take long. But of course, we were also the authors of the language. So if you're unfamiliar with the semantic pattern language, it might take a bit longer, of course. Okay, so thanks a lot, Martin. We will now go to the next presentation. If you're interested, there will be a pop-up link to click. Bye-bye. All right, thank you. Thank you. So now you can see the pop-up link.